And so I'm here to talk to you a little bit about the internet as itself, and then part of the research work I did in my PhD towards alleviating some issues that arise from this. So, the internet, can I get some definitions? So, a definition from the right.
The internet is basically a bunch of servers. No, that's World Wide Web. The internet is basically a load of sites.
A bunch of sites. Anyone from the left?
A wide area network.
A wide area network. Someone from the back? Anyone from the back? Yeah, at the very back there.
Connection, basically, a pile of computers that are all connected together, so it's basically a network. A lot of networks that you can access.
A large series of tubes.
A large series of tubes. This man's playing too much Mario. Okay, so the internet is the biggest connection of interconnected networks we have. It's a massive connection, well, a massive interconnection of massively interconnected networks. So you can just keep adding the word massive and interconnected. Essentially, it's the same thing from your desktop to your hub, times many millions. So the way a lot of people look at this, though, is the internet is what we do on it. It's the big blue E, the weird little cat thing, or that robot from Portal. So, in reality, it's a lot more complex, but most people view it as a big black box. So, this is the internet, and that's going off screen. That's the internet. Does it make sense? Yes, no, sometimes. Yeah. So we've got clusters of densely connected nodes, and then out towards the end here we have you. So large interconnected sites in the middle, a slightly narrower region around here where we've got interconnected things, and then the edge network which actually connects to us as people. So at each stage we've got this kind of three-layer structure where we've got dense interconnections, less densely connected, and then the roots. So you can think of it a lot like a tree, or some weird forest of trees where the trees connect to each other. So if we pull this out, something that makes slightly more sense, you can see there's a bunch of networks in the middle, a lot of them in America, then fanning out towards Ukraine, United Kingdom, United States, Poland, and we get the big connections there, coming down again to the tree-type structures. So the internet is very self-similar in that it looks like itself, and the interconnections are largely on a global scale. You do not actually have a connection to Google. You have a connection to a friend who might have a connection to a friend who might have a connection to some guy that once knew a guy that worked at Google. So, this you've probably seen before as an idea of how the internet is supposed to work. We have ASs, which provide connectivity. And we draw this beautiful graph where we have a guy at the top who connects to a guy below him, connects to a guy below him, who connects to some kind of endpoint network where this is where we live. And when we shove someone like BT in the middle, so the UK, let's move down a level, instead of having this, we've got this huge big black box in the middle where BT sits, monitored by the government, and says, you will be in the middle and you will take everyone's traffic and forward it to the endpoint networks. So, let's ask a question then. Does everyone know who the three volunteers are?
No.
No. Can the three volunteers make themselves known? Okay. So, there's one there in green, in a sandwich, and two reds. Okay, so if I throw a ball at someone, we come out and the ball from around, are you? Okay, can I get a volunteer from over here? The guy behind Dominic. How would you get a ball over to him?
Chuck it, yeah.
You're going to chuck the ball, okay. So, good. Try not to hit anyone.
Well, it'd probably be easy just to pass it.
Possibly, yeah. So, you immediately form some kind of interconnected network where you pass by what you believe is the shortest route. Yes, he is recording it. You know. If we pass the packet back, it takes a different route back. and nothing is guaranteed. You don't have to wait for the camera. And hopefully, the packet comes back to me. And it does. If we toss out something else, so... Excellent. This man has now stolen our packet. Security in action. Always catch your own packets. So, if we now tell them how the internet actually works, what you've got to do, you're an endpoint network, you've got to pass it to the people in red first. So I'm going to pass the Mars bar to someone of your choice. So who's the person you're passing it to?
None of you can read.
Person over that direction.
Person in that direction.
Yeah,
No, who you want it to end up at.
the person in the red shirt over there, the random.
You're giving it to him.
Yeah.
Okay? So we're now talking to network infrastructure. And he receives his Mars bar. And now, who are you going to pass it to get it to someone over here?
That guy waving his hand.
Okay, you're passing it to the guy waving his hand. So you've got to get it to the lady in red. And now it goes down. So, this Mars bar is really getting confused. Okay, so now we step up to what the internet actually does, and the only connection between the man in red and the lady in red is the man in green at the back, the internet exchange down in London or similar. So, this man in red is Janet, the university network in the UK, and this lady over here will make her Sky. So, she's your home connection, he's your university connection. So, we have two friends who like each other. Do we have two people that like each other? There we are. You two guys in the middle. Try not to take on the head of the Mars bar. Okay, so you want to exchange Mars bars. How do you do it?
Do we have to pass it around the room now?
Yes.
Direct yours that way, I'll be mine that way.
Yep, so you've got to pass to that one because you're on Sky. And he's sitting right next to you and is on the Janet network and is passing it over there. And this is how the internet actually works. Despite the fact you're neighbours and should know where each other are, and you're right next to each other, you should just be able to pass it off. You could have got a land cable, it would probably have been faster. That's the point. Okay, so as a reward for our volunteers, we somehow managed to make a Mars bar go to the lady in red, who represents Sky. Catch someone? To the Janet Network organiser and the Internet Exchange in London. Big catch. You're supposed to pass it to the guy in green. Yes, the lady in red is her Mars bar. So, what actually happens is this. This beautiful hierarchical structure does that. So people are spread around the country in some kind of geographic fashion. So in this case, we have some Aberdonians, some people from Edinburgh, Newcastle, Birmingham, Londonites. And what happens is we try and send a packet from Aberdeen. Oh, it's going to London, and all the way back to Edinburgh. So we're travelling about 900 extra miles just for the fun of it. So there goes our great connection for our on-live gaming service. When we return the packet, it should, goes back via London again. This internet exchange is getting a lot of use. And back to Aberdeen. Truly it made more sense if the packet went there and came back. So our two friends there could actually just literally pass a LAN cable between their window and say, I'd like to send you some data. Yes, would make more sense? So the internet as a whole doesn't really make a lot of sense when we take the theoretical model and move it into a real-world geographic model. So this is our silliness. And you can test this. I did it from my home when I was up in Scotland. routing to the University of Edinburgh. It goes from 20 miles from Edinburgh, a 900-mile trip down to London, a 900-mile trip back, and then I can get my file off the University of Edinburgh. So my data is travelling a significant amount of distance, which even at the speed of light is still quite a bit long. So, think about why we care about this. So, here's a picture of TV usage, and internet usage, and iPlayer usage. So the beautiful thing about this picture from the BBC is the scales are completely different. So this TV peak, there are approximately 26.9 million people watching EastEnders. You laugh, but the power grid does actually have to watch EastEnders, because when there's an ad break, there's a huge power spike as people put on the kettle. So this has real world effects. What we see, the internet peaked slightly earlier, 28.9 million users. This is mostly people just in work browsing Reddit. And then the iPlayer peak is slightly later, as people get home, walk the dog, feed the cat, avoid EastEnders, and then watch it an hour later. And this peak at this moment is tiny, 216,000 users. However, if we think about this, the internet's growing between 70 and 150% every year. We're connecting more and more people and more devices. You'll hear buzzwords like the Internet of Things. We've had an 81% video streaming growth per year and 26 times growth in mobile data usage. So all of you sitting here are probably at some point going to stream some kind of movie on your mobile phone. There are perfectly legal streaming services. I didn't say do it illegally. Yes, we know you've already tried to steal a Mars bar. So, at some point, you're probably going to stream a movie. At some point in the future from there, you're all probably going to stream a movie, and you're all probably going to try and do it at the same time. And at that point, the internet probably falls over. If we take something like 40% of TV users, we end up at 8.4 terabits per second for low quality, high definition TV. So, think of it as a door. How many of you can fit through this door at the moment? 5 of you.
I can look at a closed door.
I don't know, you said it. Okay, so that's our current internet situation. We have this architecture built around us, and someone thought the biggest pipe we would need to put in was approximately 6 feet wide and can take approximately 5 people when not closed. The problem is, all of you want to get out at once, because none of you are nice and have thought, I shall let you go first. Or have done what Dave has done as a Canadian, and said, no, you go first, no, you go first, and resulted in some kind of evil, vicious hockey match where everyone died. So, if we scale this up, ADSL, so your typical 8 meg connection, gives you about 3.5 meg. So you can stream one thing if you're lucky. Up to 24, you can get 2 streams at the moment. Up to 10, up to 20, slightly better. And then if we think 720, low quality, 3 meg. 1080p, 5 to 12 meg per second. So we're already pushing 24 meg ADSL to the max. Blu-ray, 54 meg per second. Naive 4K video, 108 meg per second. And the way people like Sky implement 3D, they just send 2 copies of the video. Great plan. So we just double this. So the scaling we're probably looking towards is something like 216 megabits per second per person per view. So when you're watching the TV and also streaming a movie on your iPad, because you do that weird multitasking thing, you're now at 416 meg per second. And pretty much, you're the only person sitting at the bottom of your network who has any form of connectivity in the Midlands. Everyone else doesn't get a sign. They just get a weird loading page that says it timed out. So we could easily see a situation where the entire infrastructure of our country's network happily falls over and dies. It's great. And if we look at this, the 2010 World Cup, we got 900,000 users watching the World Cup. On average, the users have got about 7 minutes of delay, up to 14 minutes of delay. So by the time the rest of your friends have seen who won the World Cup, you were still waiting there before extra time going, please score, police score, and not know what's happened. Then your friends phone you up, because the telephone network is fine, and say, England won the World Cup! Why does everyone laugh at that? It's happened before.
What? How many years ago?
1966, so do the math.
I don't watch football.
48 years.
Well, then all day.
So, if the scale to meet demand, scale to meet demand, at 3 meg per second, I want 8.4 terabytes of speed. 100 terabytes for Blu-ray, 200 terabytes for 4K, and if I want something fun, 400 terabytes. If we make it 100% of viewing, so we replace TV entirely with internet streaming, we're looking towards a petabyte of streaming data per second. So, big numbers. So, put it in context, the internal bandwidth of the UK at the moment, across the whole country, is about 2 terabits per second. And our end goal is 1 petabit per second. So we're only out by a factor of 500. It's okay. If we aggregate 50 people onto the same connection as we do, we're kind of stuck because we've got to increase that by 50. So 50 to remove contention, 20 to handle a single user household to stream things, 2 to 10 for non-media tasks. Presumably you'll upload to your Dropbox, you'll be downloading some random files and whatever else young boys do in their laptops at home. So, huge increase. So we're looking 50, 1,000, 2 to 10,000 times the bandwidth at some point in the future. Does it really make sense to do this? Someone from the left, does it make sense to do this? There are only 3 answers, yes, no, or maybe.
No.
Got a no. From the right?
Yes.
Yes. From the back? Maybe. And the tiebreaker from the front? Nah. Excellent. So the NAS win. It doesn't really make sense to keep scaling this, because then someone comes along and goes, well actually I want holographic video, and it's going to use up 100 times the bandwidth. And the little guy who just built your network and dug all the trenches and put everything in, turns round and says something that probably shouldn't be on video. So, it doesn't really make sense. So, we've thought of some solutions. We've got edge caching, so we move content towards the edge of the network. The only problem is, the way we consider the edge of the network is the exchange. So, 50 miles from your house, so aggregating about 5,000 people somewhere. Not very useful. Interconnection network caching between networks. So what this lets us do is, instead of having to pass the man in green, the people in red can pass between themselves, and it makes the traffic slightly better. Problem, cloud computing growth. So I'm sure Dave or Tommy has ranted about cloud computing being a buzzword. Does anyone actually believe in cloud computing?
No.
Hey, well done. It's a great buzzword, but large-scale distributed computing. So at some point we're suggesting that the best thing we can do is transfer more data through the internet. So at the moment, if you want to send large CT scans or similar for medical data, how do you do it?
Print it off and physically pass them.
Okay, so we've got Bluetooth, print them and mail them. Zip file. Okay, the easiest way to normally do this is you take a hard disk and you shove it in a carrier box and you give it to a man on a bicycle and he cycles across to the other hospital, who take it out of the box, plug it into their server, and you get great bandwidth but terrible latency. You could also attach it to a pigeon and it's still faster than the internet. So, in the grand scheme of things, large-scale data requires large-scale bandwidths, which we're not really good at providing. Peer-to-peer supported services, great plan. We will reduce this congestion by making you talk to your neighbours. Yes, we saw what happened when 2 neighbours tried to talk to each other.
You never got them.
You never got your Mars bars back. Okay, who's been stealing Mars bars?
I passed mine down and it's gone.
Okay, there should be a Mars bar for each person in a t-shirt. These 2 gentlemen and the guy that managed to convince everyone that he should be the first Mars bar owner. So, again, peer-to-peer doesn't work in the architecture we have because everything flows through the man in green. What we could do is localized routing. So networks like Janet, which run sensibly, if I want to send data to Nottingham, it doesn't go, I think I'll just walk over to London, up to Birmingham, over to Canada, and back to Nottingham. It actually routes from here to Nottingham. But it's one entity which is paid for by universities and routes sensibly because they actually care. The government has enforced other things, so localized routing becomes pass it to London and let London be local to everyone, which doesn't seem to work. Endpoint network caching is what I'm suggesting, together with properly localized routing. So if these two gentlemen want to watch EastEnders, then all they've got to do is look towards the closest person who has it and actually get it. So if the gentleman in red behind them has a copy of EastEnders, because it's his secret, I don't know, weird thing that he likes to do, sit at home watching EastEnders, when they suddenly decide, we should watch EastEnders tonight, they don't go, who's got a copy of EastEnders? Okay, who actually watches EastEnders? Okay, so for this guy, okay, so he passes it to the man in red, passes it to the man in green, passes it to the lady in red, passes it to these two guys, in separate streams using twice the bandwidth. Instead, the man in red gives them a copy to the guy with long hair, who then passes it to his friend, also with long hair. And we've got a lovely transfer which uses bandwidth only up in this tiny little area, and the rest of you don't care because your data's not affected by whatever they want to do. So they can share EastEnders amongst themselves and have their little core network, fast games, whatever they want to do, and not affect the rest of us, which seems like the ideal situation. So, in the grand scheme of making acronyms, since any PhD has to produce at least one good acronym, I wrote Hunter. You kind of got the feeling this was created from trying to find an acronym. So, Hierarchical Network Topographical Routing. So the idea is, let's make the routing reflect the geography. So we don't pass things to London just because it's funny, unless we want to, in which case we can. So, attempt to aggregate networks, create largely static groups of users, allow local service and content, allow ad hoc global routing capability, enable minimal distance routing, enable effective area multicast, and interact with existing networks. So just a small task as we go through things. Let's make the internet work. So, what we can do with geography is we say that most people don't move very far and they don't move very fast. If you attended the Vice-Chancellor's meeting yesterday, he told us all that he's successfully lived on one street for about 45 years, but he did move from number 6 to number 30. So, an average user will move maybe once every 10 years, and that's about it. So, we don't need to really track people running around, and even if we do, humans are slow. We really don't move very fast. Even Usain Bolt's only going to make 10 metres in 10 seconds, about 100 metres in 10 seconds. Car. Is a car fast? Okay, 60 miles an hour. A mile is 1,600 metres, 60 of them, 96,000 metres. Over 3,600 seconds is not very fast. A jet, 600 miles an hour. So we're still talking, if we can track it every 2 seconds, it's still going to be within your average cell phone tower distance. It's only going 600 miles an hour, that's 10 miles a minute, is a mile every 6 seconds. Seems reasonable to track. Nothing in the world that we actually do is fast. Even the fastest aircraft kind of fall apart and make them go more than about Mach 3. So more than 1,000 miles an hour and things start to fall out of the sky because they get really hot and explode. So nothing we do is fast. People don't move quickly. Allow local service and content so our EastEnders lovers here don't affect the rest of us. Ad hoc global routing. So does anyone down this side have a friend up on the right? Does anyone on the left side know the name of anyone on the right side? allow global ad hoc routing capability. So what we'd like to do is be able to say, I don't know where Dominic is, can you pass this to Dominic for me? And eventually you'll pass it over here, and despite the fact that none of these people know where he is, you'll say, he's somewhere on the right side, and the Mars bar will slowly reach Dominic. Which is what Royal Mail does. We've had pieces of mail delivered that said to the guy who used to own a camper van beside the river, who was here over summer between 1974 and 1975 and had a brown dog. And Royal Mail has delivered this successfully. That's what we'd like the internet to be able to do. Actually deliver content to us no matter where we are, simply by knowing roughly where we should be. So if I knew that Dominic was on the right side of the room, where's he going to be 5 seconds from now? You want to start walk, Dominic?
Okay.
1, 2, 3, 4, 5. He's still on the right side of the room. He's slow. In this time, our Mars bar has made it to Dominic about 1,000 times. Or our packet has, our Mars bar probably got stolen by someone over here. You can sit down if you want, Dominic. So,
I want.
continue to stand if you wish. So, people don't move much. Enable effective area multicast. So again, this really comes down to government legislation. Theoretically, BT can multicast stuff. But all of the providers, so our lovely lady who is Sky, and our gentleman who is Janet, have said, yes, we'd love to multicast to this entire front room, but we only want to pay for one stream. So the network providers have said, screw that, you can stream to them all separately, yes, it'll screw the network over, but now we get paid for 30. So economics and the way the government set this up really screws over the network design that we have, because there's no way to bill for that multicast stream to these end users, because to Sky and Janet, they appear to be the same. Because there's lovely interconnection network that hides everything. So we've got a whole bunch of things that don't even relate to technology that screw up the internet. And interacting with IPv4 and IPv6 is useful. An internet has a rough usability factor equivalent to the square of the number of users. So IPv4 with something like 2 billion users has a usability factor of 4 and lots of zeros. IPv6 with a couple of 100,000 users has a score of not a lot. So if we want to talk to each other, which IPv6 and IPv4 don't do very well, we need to actually be able to interact with things as a native measure of doing it. So being cautious of time. It's an hour or slightly short.
You've still got about 20 minutes if you need it.
So if we consider naming identity, rather than doing just dots, let's consider who is this node, so who is Dominic, address, where is Dominic logically, and routing, where is Dominic physically. So how do I get messages to Dominic, and who should I be giving it to pass it to him? And naming, what is this node? So if we want, we can rename Dominic something easier to remember. So does Dominic have a nickname?
Dom.
So he will be called Dom because it is shorter and easier to remember. So IPv4 and IPv6 do something like this. IPv4 is variable, and you'll cover this in your networks lectures, but somewhere between 8 bits and 24 bits for the number of networks. IPv6 decided the best way to do this was say that everyone's home network can support a maximum of several trillion devices. You've all got a couple of trillion devices at home, don't you? Yeah? Excellent. At least that guy does. So, IPv6, we said, let's make them bigger. That way we won't run out of space like IPv4 has been doing for the last 30 years. Unfortunately, they've done this weird split that doesn't really make much sense, other than so we can use our MAC address as an auto-configured address rather than just picking a random number. So IPv6 as it stands doesn't really make much sense over IPv4 given the number of things they've stripped out of it. And that's an entire course on itself, so I'm not going to cover that. So, separate names of identity and move away from ISP-centric. So, these two gentlemen, who are on Sky and Janet respectively, can just pass things between themselves. because they're physically connected at some green box about 50 yards from them. Makes more sense, yes? So if I throw a ball at someone, can you pass it to your neighbour? That was hard. And I couldn't do that again if I tried. So, we can route globally if we get rid of this whole concept of IP. We can move services down the network, so our fans of EastEnders can hide in their little corners and not bother the rest of us. Does anyone play Warcraft? A couple of you. Okay, so if I want to distribute your Warcraft patches to you, who's a Warcraft player? This guy over here. Excellent. Take one over here.
That was your fault.
That was my fault. Okay, so I'm passing these out to you individually. Wouldn't it make more sense if you're now going to give your friends these? So how many people up there play Warcraft? 1, 2, 3, 4, 5. Should I toss 5 more balls to them, or should this guy who has it pass it to them? You want me to toss 5 more balls? Is this because I don't have 5 more balls? Evil people. It makes more sense for them to share it locally and save the bandwidth in the rest of the network. So, we'll pass around the balls till you all get your updates. And we can simplify the hardware design of routers. So, rather than doing this complex thing where we bounce things through London and stuff goes up and down the country, we'll build a tree out of it and we'll pass to our nearest friend, either up or down the network. So this, which is what the internet looks like, becomes this. We've got a small number of nodes sitting in the middle, continental level routing. So we consider America, South America, Europe. We've got aggregation level routing. So within Europe, we probably have something like France, Germany, Luxembourg, Liechtenstein. And then we move out to here. So then we have Fred Fluselberg living in Derby, in the United Kingdom, inside Europe. And we know exactly where Fred Fluselberg is. And if any of you don't get the joke, please consult Fred. Can Fred please put her hand up? Excellent. So, we take the simple abstract model we talked about earlier, continents, countries, end users, and we make it make sense, rather than this idea that Fred Fluselberg is address 127.5.4.1 is sitting next to the lady in a sports top, which is 5.3.7.2.
Who's wearing the sports top?
The lady sitting next to Fred.
It's a
Sorry?
jumper.
It's a jumper. Sorry.
Honestly.
So it's quite difficult to see from down here. There's bright lights and everything. So we start to make sense. So this is what we want to do. We're going to create addresses that look awfully like this. So just bits of ones and zeros, which the routers connect or together, and be really fast at working things out. To make it easier for us, we can break it down like this. So this was from my PhD, this is where I lived. So UK, Scotland, Lothian, Edinburgh, University of Edinburgh, King's Buildings, Engineering, Alric Building. It looks awfully like a postcode. So if I'm here and I move somewhere else, I'm probably still quite close to engineering, so my data can find me. If I move really, really fast, I'm in a car, I'm still in King's Buildings. If I move really, really fast on a plane, I'm probably still somewhere near Edinburgh, or worst case scenario, Scotland. So my data can find me no matter how fast I move. So if we start to think of the internet as a geographic entity, rather than this abstract cloud of stuff, or a pile of tubes, then we start to make sense of the internet as a whole. So what we can do is, we could do all this on traditional IP networks. We just build more things on top of it till it falls over and dies. And that's the current plan how we work. This plan was make it easier to parse the network in real time. So if everyone stands up and moves seat, one step too far. Okay, so if everyone theoretically stood up and moved seats, in a traditional internet environment, this would be a nightmare to work out where you all are, because I assumed you were all fairly static and would just sit here. Under this system, I don't care. All I have to know is where the root of the network is, so Mr. in green, who will then tell me where his neighbours are, and eventually we will build a tree that reaches the furthest reaches of this lecture theatre or the United Kingdom, and will automatically reconfigure the network. And because we haven't changed your names, so we still know that Dominic exists, we still know him by his alias Dom. So if Dominic moves over here, we can still find him, because eventually he'll say, oh, by the way, I moved over here. He leaves a forwarding address, and everything works nicely. And to replicate this, he has moved one seat to the left. Very good though. Large address space allows for growth. It's entirely parsed in numbers, and it just grows. So we're fine. We don't have that weird split between host and network that we do in IP, which, seriously, does anyone have several trillion devices? Dave. That doesn't actually surprise me. Dave collects everything from everybody, so if you ever need anything recycled, our office is the place to bring it. Decentralized management of address space on a per-node basis allows for dynamic reconfiguration. You can tell this came from a PhD. There are many buzzwords in one sentence. So, the idea here is, again, does this man in green matter to us? In a network sense, not as a person. Does he matter to you? We've got a head shake here. No, he's right. We don't care. I don't care that that lady at the back is Sky, that this gentleman is Janet. All I want to know is that my packets can reach Dave, who's sitting next to me. And if we can make that more efficient, why not? Things are getting faster, processes are getting cheaper. We can actually do distributed billing rather than everything flowing through these three people just so we can build them. Address space is not wasted. So if we have my house at home, I think my parents have probably about 12 devices connected to the internet. At worst, they need 5 bits of storage space. IPv6 gives them 64. So there are 59 wasted bits in my house alone. So why build a big address space that takes more space to parse, more work to do, if we're never going to use it? You know, my parents are probably never going to approach 128 devices. So even 7 bits is probably a bit excessive. So, benefits of localized routing. Let's consider streaming. Video on demand, one stream, it doesn't work very well. So, total cost, if we do something like Hunter, access level caching, we get very low levels, so very cheap to do, and there's virtually no slope to this line. So if the EastEnders guys suddenly have a party, and there are entire people around them, so can the people around them put their hands up? Come on, spread! Let's get at least 50 of you. Come on, hands up, in the air. We have like you just don't care. Okay, so now, instead of sending 50 streams, we're still here. So that additional load on our network has cost us maybe 5 pence, rather than costing us several thousand, just to provide that extra data. So if the entire class suddenly puts its hands up, it costs us, again, on the order of pennies to do this, rather than thousands. Because the limit, there's a cap to how much we have to stream, because we can move infrastructure down the network. So EastEnders is now provided by that guy there, to everyone that's close to him. And he's happy about this. So, the logical conclusion to this is SkyNet. So, the conclusion, yes, comes down to SkyNet. So, James Cameron suggested that SkyNet will be a large number of robots attempting to kill us, other than those rebels they could never find and just hit with the nuclear weapons they hit the rest of us with. Go figure. So, your average skybox is between 500 gigabytes and 1 terabyte of size. About 250 gig to 500 of this is reserved for anytime content. So, you can get stuff available anytime without them having to send it to you. Sky, approximately a 50% population coverage, which is quite scary. And the average household has about 2 boxes. So in effect, there is one box for every household in the UK. Yes, Sky have that kind of penetration. This means at the bottom of the network, so attached to their houses, there's something like 25 terabytes of space available, which is between 2,500 and 5,000 movies, without ever sending anything else. So simply by using Skyboxes, we could distribute the whole of Netflix for free. Yeah? Does that sound good? Excellent. So we can get huge benefits, and it's effectively free to us. We're not paying for extra infrastructure. We're utilising boxes that already exist, so we can get free benefits for very little cost. Mobile device streaming is costly. Again, if you try and stream from your device, it goes up, down, left and right, and does weird things. If you've ever tried to stream on a bus, it goes through an even worse route. And I can provide diagrams if you really want to see those. So, why not, if this gentleman, with also long hair, is near these gentlemen's Wi-Fi, or near their connection, why can't he watch their EastEnders rather than his? Does that make sense? Does it seem fair? Yeah, it would make a lot more sense if we streamed from a local source that can provide it, rather than, well, it's my EastEnders and therefore it has to be streamed from my house in the Caribbean. I wish I had a house in the Caribbean, I don't, so that stream's not going to work. But it would make a lot more sense to log in anywhere and stream locally. So EastEnders flows across. So, future, current networks focus on static nodes. Nothing ever moves, the network is fixed. It's awesome. Mobile data is screwing this up a bit. Video streaming is screwing this up even more. So, we want to be able to move. We want to be able to watch movies as we go. If you're watching Despicable Me 2 here, and you're travelling to Nottingham, I could probably send half of the movie over to Nottingham and stream it to you from there, because the movie is 90 minutes long. So you're not going to get through the half the movie by the time you reach Nottingham. So why would I bother provisioning it to Derby? So we can do things and actually move around. We can map network connections and actually model movement and move data to where you want to be. So if you were watching Despicable Me at home and then you're coming to the office, we could just forward the rest of the video to the office so you can watch it when you get in. Yeah? Good plan? Do it tomorrow? And that's where I end with word questions. Yes?
You said like over there, the person like gets the patch and then he distributes it around.
Yes.
Like, wouldn't that really affect his connection to the, you know, like if he wants to watch something?
Not really. So again, if you think about it, the entire bandwidth is connected. So if we assume you've got an 8 meg connection to the exchange, there are 50 people who share that. So at any given time, you're really only allowed 1/50th, so 2% of the allowed bandwidth. You will see it as more because it's very unlikely that someone's browsing web page at exactly the same second as you. So it appears you get your whole bandwidth, but you actually don't. This is where video streaming screws up the network. So at any given time, it is very unlikely that any of these guys are fully utilising their connection. And so he can pass it around nice and freely. And as soon as he's passed a chunk to someone else, he can share that with someone else. And if we can multicast it, he can send the whole thing to everyone at once without worrying about, you know, I can only send it to one guy at once because the lady from Sky says that I have to be billed in some weird method for this. So it comes down to statistical aggregation. We never actually use much of our bandwidth at any given time. And that's how they make their profit just now. Yes?
Wouldn't a structure like this significantly increase risk in terms of network security?
Not any more so than you've already got. When anyone who actually wants to, well, sorry, we'll start with the original fallacy. The network is the insecure point, is how we're always viewing networks. In truth, the endpoint is the problem. The major flaw in network security is between the keyboard and the chair, which is problematic because we go, let's secure the network. And then, you know, your dad comes along and goes, ooh, free XE. And installs, you know, the Bing toolbar, the weird search toolbar, the other toolbar, and his internet browser looks weird with these 17 toolbars and the thing that sends his data to, some guy in Nigeria. So the network isn't really any more less secure, because what we want to do is secure the endpoints anyway. So the data should already be secured in the middle, which was the plan for IPv6, but then we removed it. And secondly, anyone that actually cares enough to steal your data can do it. So the police regularly tap everyone's network connections. The lady from Sky will happily give your data to the police. Heck, you don't even have to ask her, they'll just cut her cables, insert a device, and steal the data before she gets it. So anyone who wants your data can steal it. So network security as a concept is, well, it's really overrated when you consider your data's already flowing through a guy who pretends he's the internet. So do you trust the man in red?
No.
So if you don't trust him, then this is no more insecure, because you're already trusting all of your security to that guy. Any more questions? Okay, so the people with t-shirts and Mars bars can hang on to them, but I would like my tennis balls back. And thank you very much for listening.